Good morning. How are you all today? Can you hear me? It's not very high, is it? How's that now? Better? Worse? Okay. So this is week 6. No, 7. My goodness, time flies. We are halfway through. Another half to go. So you've had 3 tests so far, and then 3 more to go. How are you feeling so far? All happy? Still good? Still with me? Great. Not much to go now. So what you've seen so far, you'll find the idea is similar for the rest of the course. We're still going to use similar kinds of models. So there's 2 categories of data we're looking at. The first is binomial data or binary data. So that's at 2 levels. We saw the first level last week where we looked at essentially single binomial observations or single Bernoulli trials, if you like. So we've got individual observations in each person. We extend that today where we've got not just that, we've got actually full binomial observations, and I'll explain that as we go through here. The next thing that happens from here is we extend that to count data. We've got Poissons, we've got counts of things happening. No longer binary binomial, it actually counts 0, 1, 2, 3, and so on and so forth. And so similar models apply there. They're still log linear models in some sense. Some things change a little bit, and some things are a little different. Model diagnostics and things like that need to be a bit different as well. Some extra things can be different, and some things can go wrong. Those kinds of things we look at as well. Rather than that, mainly the same. Nothing much too different. So that covers the next few weeks of lectures. And the last few weeks are meant to be for maximum likelihood estimation. That's more mathematical. So we look at the ideas of things, at least try and get some likelihood equations written down. And for those who have done more calculus, you can actually do this thing and actually work the whole thing out to the end. If you don't do it with this class, you'll do it somewhere else. If you're interested, you can see me sometime. We might do a special session on that. Other than that, we'll hand wave a little bit, and we'll look at how to maximize or obtain maximum likelihoods by using R as a tool, how to plot things out, and how to sort of look and see whether things actually look okay. Maximum likelihood in general is a hard topic because it is more mathematical, but more than that, unfortunately, there is no guarantee that you'll actually get a maximum. And if you do get a maximum, there's no guarantee that's the one that you should be looking at. Are there more maxima than just one? And have you got the right one? Those kinds of questions are more difficult. So we're at 10 o'clock. Let's start this. What I've also got is a video. That's actually a long video. We'll cut the thing out a little bit as we go through. But that's also interesting for you, as we'll see as we go through. So today we're looking at regression, logistic regression again, for binomial data. So as we said last week, we looked at binary data, 1, 0. Now we look at full binomial trials. The idea here is, suppose I toss a coin 10 times, I get something, the number of heads I count there, and I can look at that as an individual trial. If I repeat that, so the first trial is going to be an observation on a binomial distribution. How many heads out of 10 tosses? I repeat that, or somebody else repeats the thing, and you take the same coin, or in principle at least, and toss at him 20 times. Oh, that's all right, you've got them in front of you. That's because I haven't connected it. Thank you. Until now you can see the slides, I hope. Where's the wire gone? This is go. Where's the connector? You see it? Oh, here it is. So yes, we're looking at binomial data, as I was saying. And so we'll have a brief look back at what we did earlier with the binary responses, and then take a look at similar models for binomial counts. And it's a matter of how you've organized the data as to what you put into it and how the model fitting is organized. And then we'll take a look at the usual stuff. So once you've got the basic idea of how linear models work, everything else works in a similar way. We'll finally also look at model assessment. All models are wrong, as they say. Some models are better than others, but certainly if your model assumptions don't hold, things go crazy. One of the things that went wrong with the global financial crisis in 2007 or so, if you're still there, sort of a little bit younger, I suppose, was that the models that were used had assumptions that weren't satisfied. And so models don't hold in that situation, and people just kept using them and things went crazy. That happens quite a bit. We see quite a bit of that and things go crazy. So the components of a generalized linear model are this. There's something called an exponential family. We don't spend much time on that, but it's just worthwhile hearing the words and knowing that this idea exists here. Essentially anything that can be written in some exponential form. The normal distribution is easy because we know that the normal distribution has, for the normal node 1 at least, fz, the normal node 1 distribution has PDF that looks like this. I make sigma equal to 1, so that disappears. And then I actually have e to the negative x squared on 2. So that's exponential to start off with, but almost anything I can write in exponential form in some particular way. When I do that, some things come out of that, and we'll discuss some of those as we go through here. The idea here is that we're going to have a linear predictor here, and this predicts something, exactly what depends on the particular model we're using, but it's the usual linear regression here, and this thing here is what we're looking at. The link function here is going to be what we're looking in this case. Our link function is the logistic function of the probability of success pi I, and the pi I here, the I being the observation I, so it depends on the individual I we're looking at. So we're modeling here the probabilities or the logistic probabilities for the person or individuals we're looking at according to the other measurements that characterize the data. And in this case, what we're looking for here, that the expected value here of yi, which is the observations, data y1, y2, yi, is pi I, which is the binomial probability, and there's the inverse of this link function over here, inverse of this particular model. So those things we saw last week. So if you compare this with what we call the normal regression model or Gaussian regression model, in the Gaussian regression, certainly what we expect is that, as it says normal probability model here, we're expecting that the residuals will be normally distributed. At least the residuals should be normally distributed. And the link function is identity because we actually model the mean itself. Here we don't model the mean. The mean here is pi I. What we're modeling is not pi I, but log of pi I over 1 minus pi I, the odds here. In the normal regression, we actually model the mean itself, and so there's no problems with the link function, that's identity function. And the variance is assumed to be constant. We say the variance is assumed to be the same for all the data, or at least we can say the residual variance is unchanging. Whereas for the logistic regression, we know certainly that we now have a binomial case here. It's a logistic link function, and the variance isn't constant. It depends on the mean itself. For the normal distribution, the mean and variance are entirely unrelated, or they should be unrelated. That's the assumption. So these things are different here. Look at the ideas behind Gaussian response and logistic response. For Gaussian response, your particular data will be continuous. Logistic is just 1, 0. It's binary. And the other data can be similar or the same. For example, here I'm looking at the height of a person against the variables of sex, treatment, and age diagnosis, whereas here survival, which is now binary response, again based on those particular variables. Can be the same or similar in that sense. So those things don't matter. Other than that, the model, as I say, will be modeling either in the normal case, it actually models the mean. In the binomial case, it models not the mean, but something else. And we saw how the logistic function behaves. It goes towards infinity and negative infinity as we go from 0 to 1 for pi. And so that all is fine because we could turn something that was 0, 1, or between 0 and 1 to something that's a range of real numbers, which we can now actually model by a regression analysis. The regression we know doesn't necessarily hold values between 0 and 1. It can go outside that, and we allow that now by this logistic model. Data we had was 1, 0, probability pi I of success, and 1 minus pi I of failure. And the probability mass function for the Bernoulli is this, is pi I to the y I 1 minus pi I to the 1 minus yi. So when yi is 0, this first term is 1, and I've got here 1 minus pi I. When yi is 1, this second term here, that becomes 0, so this whole term becomes 1, and I've got pi I to the 1. So that makes sense. In other words, what I'm saying is, from this particular equation, you should be able to get fairly easily that y of probability of pi I equals 0 is 1 minus pi I, and probability of yi equals 1 should be equal to pi I. That should be easy to see from there. And pi I here modeled with the logistic regression model, if I turn that around, I get here that pi I is exponential of beta naught and all the rest of it, if it's just simple linear regression in this case. Okay, so for binomial counts, things are a little bit different, but basically the ideas are the same or similar. Here's an example we look at. This is from the book itself, the Stat Sleuth, page 110. It may depend on the edition you've got here. But here, this person is looking at this particular set of birds here. The idea of this particular islands, actually. And the idea is that preserving certain habitats in their natural state helps slow species extinction. And it's a matter of deciding whether you would want to have a few large ones or just a lot of small ones, which is better to have, a few larger habitats or just a lot of small ones. So the data here comes from these islands they're looking at, the Crunit Islands. You can work out where it is and tell me. And so this has retained its natural habitat, and so we're looking at things as they are, not artificially put together. So what we're looking at here is the number of species at risk. This is bird species at risk, and so this is actually the number of species that are on the island. Anything that's still there is at risk, and we're looking now at also the number that are extinct since 1959, if they have not been found in the last decade or so, and we're also looking at the area of each of the islands. The idea is here, is there a relationship between the island's area and the probability of at-risk species becoming extinct? So the at-risk species are those that are still there. Those that are extinct are those that have been seen in the decade from 49 to 59, and the area as we're looking at here. There's the data. It's in Sleuth, so library Sleuth, and then you've got the data itself. It's case 2101. And you've got the data, you've got the thing, the island name, the area at risk and extinction here. Now, of course, what we're after here is we want the probability of, or the odds of extinction in each of the islands. So for each island, we can obtain a probability of extinction by looking at how many were extinct out of how many at risk. Those kinds of ideas we can do very fast, but we want to relate that also to the area here. So proportions is what we're looking at, Zi over Mi. We can take a look at counts of proportions. Essentially, other where we're looking at, if you're looking at counts, we're still looking at how many we had to start off with. So Zi here is the number that were extinct, and Mi is the one number at risk. And this is, now the idea here is that because these proportions here, this Zi on Mi, is based on integer data. It is going to be very granular. Yeah, if I toss a coin 100 times and I count and I find the proportion of heads, then I know my proportion of heads can be 0, 0.01 when I get one head, 0.02 when I get two heads, and so on. It's granular, right? It's not continuous. In the same sense as, for example, I look at proportion for continuous things like proportion of body fat. That's continuous. Yeah, that's continuous, because it can be any real number over some other real number as a total. Whereas here it's granular, it's not quite continuous. And this is one of the issues when you try and do something like estimate or approximate the binomial or the proportion, binomial proportion by a normal distribution, that granularity actually comes into it and gives you extra error in there. So that's something to watch out for. So that you can expect will give us some problems in estimation and problems in the actual predictions of models as well. What we're going to do here is, as we said, MI is the total number of species on the island which is at risk, and pi is probability of a species becoming extinct on the island, and we've got Zi is a random variable representing the number of species that were extinct on the island in 1959. And it says here the observed values of Zi, which is the number of species that are extinct, is also recorded here. So the model we have for the data is for island I, Zi, remember Zi is the proportion or the number of birds that are extinct, is mi pi I. So mi is the number of birds that are on the island and at risk, and pi I is probability of being extinct. When you're trying to link that to the area of the island, so this is the usual binomial probability mass function. The mean is going to be mi pi I, and the variance is of course m pi I 1 minus pi I. We're going to model pi I as a function, in other words, a usual logistic regression function of the actual data we have, which is the covariates. So what we have here is, unlike the previous cases, we've got several binomial distributions, and we've got observations on each of the binomial distributions. The data here actually is binomial, not binary anymore as such, it's binomial. Of course, within each binomial distribution is binary in some sense, but it's binomial. And so we've got a different number of trials as well here. As you can see, the mi depends on I, the island itself. Different number of trials here as well. So that's quite a different model than what we saw before with just binary trials here. Nothing changes in one sense here. We're still expecting here that the EZI here, before it was just pi I, but it's now mi pi I, but still it's still proportional to pi I, and that's all we care about. So we can model the thing in the same way as before. The logistic regression model holds in this sense. We're going to fit that here with the covariates, whatever we've got over here in the data, we can put them all in the data here. So look at the data, have a look at this, and what you'll find without too much hard work is that you want to take a look at the number of looking at the area of the islands and the at risk. What you'll find is the area of the islands is actually quite wide, some very small to quite large, and also the at risk changes quite a bit as well, from 6 to that, and the number extinct also changes quite a bit here. Other than that, nothing much more. So you've got individual islands over here, but you can see there's quite a wide range of areas as well, and the other numbers also in the sense. A histogram or a bar plot shows you a bit more of what's going on here. So this is the first plot here is the histogram of the area of the islands, and you can see there's lots of things with small areas and some large ones. And I think I said earlier sometime, if I didn't, this is a good point to say these kinds of things. When you have a data that looks like this and is skewed, very skewed to the right, yeah, it's very, very long tail over here, then something like logging the data pulls the tail in. So data that's skewed right, but taking the log or the square root will actually pull the tail in. And I think I did say this before, you've got numbers like 1 and the squares, 4, 9, 16, 25, say. If I take a look at the square root of these become 1, 2, 3, 4. So they've actually come a lot closer than they were before. So square root is one of the transformations that pulls the tail in. The log is more severe than square root. Sometimes you should try a few things like square root, cube root, and log and see which is better. Sometimes if you do a very severe one like log, then the right skewed data turns around, becomes left skewed. So be careful. Just don't transform the data and do nothing more. Transform it and look at it again to see whether they actually have done something worthwhile there and whether you have gone too far or you've got some symmetry there. So try a square root, cube root, log, whatever, and see what happens. I'd try square root to see whether it behaves itself well. If it does, I'd stop there, but it's worthwhile looking at log as well anyway. But between square root and log, if you find it's okay, you'd use one or the other. But if you find the square root doesn't work and log is too severe, go cube root or one of the other ones to see what it looks like. Sometimes the reason is to do one or the other one in particular instances because of the context. But here you can see that taking a look at the log of the area actually does make it fairly good. It makes it much more symmetric. More than that, you see, the problem with trying to fit data to a model to a data that's like that, data becomes very sparse, and you've got little bits of data all over the place. There's no continuity in the data as such. Taking logs brings it back again, makes it continuous, so you can fit something nice to it. So there are lots of things with data here that you can look at. Another aspect is, there's another way of fitting the data here is, and this is just so that you can be aware of this thing, is one thing that we often do is we say, all right, the data is just so sparse and in so many groups over here, we actually form groups. So we turn this into categories. We can say at category 1 or level 1 of the area, 2, 3, and 4. The only problem here is there are quite a few in this category and very few in the other categories. That can be a problem as well. So it's a matter of balancing this out to see how it works. In this case, log in the data certainly looks sensible to me, and that's what you do here. So quite often you will do things like this to transform data to make it behave a bit more, and then you can use a model using the data. So you can take a look at some of the summaries as well here, but there are two variables we're going to create here. Is the log transformed data area we're going to use here. This is one of the things we can do here. We know that if you take a look at the empirical proportions Z over Mi, that's something that will relate to the area in the model as we go through this. So log transformed is one thing we'll do with the data. So here is the transformation of the data, log area and the empirical proportions, both have been calculated here. So you see what's going on is within CRUNIT, so it adds those variables to this data frame CRUNIT, so it adds to it the log area and also adds to it the empirical proportions as we've got it from the data itself. Stop there for a second. Any questions so far? All right, here is the scatter plot of the empirical proportions versus the log area, and you can see broadly speaking there is some kind of trend over here, whether it's linear or whether it's non-linear is not clear yet. You might try and fit linear to see what it looks like, but it certainly looks like it may be not non-linear as such. So there's a plot of the empirical proportions against the log of area, but there's just two variables. Sometimes looking at two variables by itself can be deceptive unless you fit other variables in there. You mightn't get the full picture. Here is the same with logit of the data, of the proportions, not the proportions themselves. And that looks probably a little bit better, more closer to linear than the actual proportions themselves. The model is simple. It's going to be the logit is equal to something in terms of the log of the area that we have got there. The glm command still works, no problems with that. And so here is the model, if you can see it clearly enough. So we've got here in the response part that we usually have here, you've got two things. You've got the number of species that were extinct and the at risk minus extinct. So you've got the at risk, so you've got the failure, the successes and the failures. Success here is extinction, right? So we've got the success and the failures. The number extinct and the number at risk minus extinct, in other words, the number that survive. So that's clear, that requires care here as to what actually goes in here. So you've got here the number that are extinct, if I call that y, and the number that are going to be not extinct, or the failures. So I've got, this is one way of entering the data in here, the other ways as well, and you'll see that as we go through here. We've got y here and n minus y is my response, and this is just a column bind, C bind of those two things. So there's essentially two variables that go into that model on the left hand side. On the right hand side, all I've got is log area. And so it tells me what the call is. The model itself fitted is extinct and at risk minus extinct here against log area. And you can see by the usual output, you can see that I've got here, I've got intercept that's significantly different from 0, and I've got log area that's also significantly different from 0. By looking at the particular coefficient straight away, I can see that the dependence on area is negative, which means the odds of extinction decline as the area increases. I'll say it again. The coefficient of log area is negative, which means that the log odds of extinction decrease as the area increases. Is that okay? That's the kind of thing we're expecting and hoping to see in your tests. The expression straight away that the logs odds, this is log odds we're looking at, log odds of extinction decrease as the area increases. The other things over here that may be of interest is just to look at the deviance residuals, how big or small they can be here. And the other thing here is that you will see, you always find this thing that we ignore for the moment, is it says the dispersion parameter for the binomial distribution is taken as 1 here. And the other thing you'll see is the null deviance is 45.338 on 17 degrees of freedom. And the residual deviance is 12 whatever on 16 degrees of freedom. So this is the deviance that corresponds to the null hypothesis. Which says there's no model here at all. So I've got my model here is logit of pi I equals beta naught plus beta 1 log area. That's what this says. And so that corresponds to the null deviance. Whereas the other one, the residual deviance, corresponds to the alternative hypothesis, which is that beta 1 is not equal to 0. So as I was saying earlier, regression outputs are based on two-sided tests all the time. The p-values you see there are based on two-sided tests. It doesn't know, it just assumes two-sided. You can decide which way it's going to go. I can see here, as I was saying, that certainly by the p-value, which is tiny, I would conclude that beta 1 is not equal to 0. And of course, because it's negative, that means beta 1 is less than 0. That's the kind of inference we can get here. So that is what it looks like here as far as the null deviance is concerned. So later we'll see this idea of how we can do a deviance test. We have seen that before, but essentially what's going on here is when I have a look at just the null deviance, if you go back a little bit, I'm not sure whether it says so here, or I can pick it up from the data as it says it, or I can actually, yeah, I can. That's 1, 2, 3, 4, 5, 6 plus 12, 18 islands altogether. Yeah, that's 18 islands. So my n here, the number of observations, is going to be 18. And you can see the degrees of freedom, the null deviance has degrees of freedom, that's n minus 1. Yeah, that is 17, that's 1 less than 18. So I've got n is equal to 18 data points altogether. So the null deviance is 1 less than that, in degrees of freedom, and because I've actually fitted an extra parameter there as well, beta 1, that's going to be an extra one taken off there. So n minus 2 for the residual deviance, 16 degrees of freedom. And so the idea here is, and we'll surely discuss this later on again, I can test the hypothesis that beta 1 is equal to 0 versus not equal to 0 by looking at my p-value here, which is 6.08 times 10 to the negative 8. In this case, I will clearly reject the H naught and say that beta 1 isn't 0. But I can also do this. So this idea of doing it this way is what's called Wall's test. It's nothing more than the Z test. As you can see, it's based on a Z test, essentially, nothing different from that. The other idea is I can see what the difference in deviance is. I can base it on residuals themselves, and somewhere the residual sum of squares. That's the similar kind of idea to what you would see in N over here. So the degrees, the change or the drop in residuals from the null deviance to the residual deviance is quite a bit here. It's about, what's it, 33 or here, 33.3 something. And so there's quite a bit of difference in that here. And so I can use that instead to do a hypothesis test, and we'll do that later on in the lectures. We'll see how that works out as well, and whether the conclusion is the same or different. So here's the model equation, the fitted model equation, that log of pi I over 1 take pi I hats here is equal to that. No problems. I can turn that around and get my pi I observed here. That's also the case. Now, we don't often actually go this way. We don't actually go here. We're not often interested in the probabilities. We're more interested in the differences between things. So if I'm putting categorical variables, I'm more interested to see how the things change there. In this case, I know that if I take a look at, well, not the logs of the odds ratio, but just the odds ratio itself, I get exponential of the whole thing, which is the top line here. And I can see, as we saw in maybe the labs or whatever else and explanations there, how we can explain the dependence on log area here. If you suddenly double the area, what happens? It becomes log 2 and so on and so forth. A bit of calculation required here, but overall you can see what's going on there. So that's the equation for the probability of extinction. Now, question was whether the reserve size affects or influences the probability of extinction. So we're looking at here at the hypothesis test of beta 1 equals 0 versus not equal to 0. As we were saying earlier, the R output gives us p values here. In this case, we will not reject H naught, and so the negative here implies the larger the length size, the smaller probability of extinction. All of those we've just said before earlier, and I hope that all makes sense here. Stop there for a second. Are there any questions or clarifications? Good? Walls test? That's Walls test. No? Meaning? Yeah? That's what we call Walls test. Yeah, it's the way of testing this using p-values based on the Z distribution. Good? Anything else? I don't like that name myself, but it's had a chance to stick. People use it. I just call it unusual hypothesis test using p-values. Names aren't important for me in that sense. So as we saw earlier, so if I've got a regression that looks like this, a logit pi is beta naught plus beta 1 log x in this case here, then a k-fold increase in x is associated in the odds by a multiplicative factor of k to the beta 1. So how does it work actually here? And so if you double it, becomes 2 to the beta 1 and so on. There are some calculations given here later on here. You can see what's going on here. So I've got this is when I've got a log over here. If this isn't a log, that'll be different as well, of course, but we've seen that before. So how does it work? So if I've got, say, I start off with area equal A, and I multiply it by a k. I increase it k-fold, ka. So I'm looking at here the odds ratio, omega ka over omega a. So it's beta 1 log ka minus log a, because you see what I'm going to have here is in the equation of for the odds, what I'll get is I'll get the ratios here become beta 1 log ka on top and beta 1 log ka on bottom, and we know that essentially e to the a over e to the b is e to the a minus b using properties of exponentials. That's what's happening here, and you can see here I'm going to use the next log laws, and I've got the log law says that log of a divided by b is log a minus log b. So I've got here a log over difference, so it becomes log over the ratio, ka over a, the a's disappear, I get log k here. It's x of beta 1 log k, and I'm going to use other log laws, so I know that exponential of e to the a to the b becomes e to the ab. I multiply the powers. So I've got here beta 1 times log k, so it becomes x of log k to the power beta 1. And of course, this x of log k is exponential of log k and exponential inverse functions. If I take the log first, then the exponential, I get the number back again. This is k to the beta 1. That's where we get this factor of k to the beta 1 from. So if a k-fold increase in area will lead to a change in the odds of the extinction by a factor of k to the beta 1. So double the thing becomes 2 to the beta 1 and so on. To obtain a confidence interval here for beta 1, if it's L and UL lower and the upper end here for the confidence interval for beta 1, if I want the confidence interval for the k-fold increase, then it just becomes k to the powers over here. We just transform the confidence interval in the same way as we transform the actual observations, or in this case, the actual output, if you like. Nothing much changes here in that sense. So those kind of things we've done before. You can change from proportion to percentage for confidence interval. The same kinds of idea happens here. The problem here note is that while the confidence interval for beta 1 will be symmetric because it's based on the z distribution, by the time I do this kind of nonlinear transformation, it will no longer be symmetric, and we'll see that as we go through here. So symmetry is lost in those kind of things, but that's not a problem. That's how we expect it to be. So here, if you double the area of the island or the landmass, then the changes in the odds ratio by a factor of 2 to the beta 1, so it's 2 to the negative 1. Now, the probability or the odds of extinction now is only 80% or 81%. Yeah, so if I double the area, the odds of extinction are now 81%. They have gone down as we expect. And this is calculations to show that's exactly the case here. So there's various ways of reporting this. You can say that if I double the land mass, then the odds of extinction are reduced by 81%, or you can say it goes down by 19%, equivalent, so it goes down by 90%, or is 80% of what it was before. Those kinds of words, as long as it's clear what you're saying, is what we're looking for. So here it takes a look for 10 and 20 in particular to do the calculations. Very important, you can look at the numbers yourself, but the idea here is still that because I'm doubling it, it's going to be e to the k to the beta 1 in this case. So you can see here the odds over here work out to be 0.15, and this is 80% of that essentially. The other way, if you halve it, of course, becomes 0.5. The factor now is a half, so it's 0.5 to the negative point, whatever the beta term here is, and that's 1.22. So the odds have increased by 22%. It's 1.22, yeah? So it's gone up by this 0.228. It's gone up by 22%, the odds ratio in this case. Or the extinction has gone up by 22.82%. Or we can say is 122% of what it was before for land mass of the area we had. If you halve it, it becomes 122% of what it was before. It's easy to say it this way, saying that it actually has increased by 22% or 23% in this case. And again, you can check that by calculations, but it's the interpretation here of this kind of idea that you've got 0.5 to the beta that's important here. Now, this idea of this k to the beta holds because I had log of area. If I don't have log of area, if it's square root of area, things will change, and I can still do the similar calculations to work that out. It takes a bit of mathematics if you like, or you can do the exact calculations using the numbers as we have over here to see what goes on there. But some things may change there. All right, so confidence interval, usual story. It's going to be beta 1 or plus or minus the z value times the standard error of beta 1. And the standard error of beta 1 is given to you in the R output. So here it is. It's the value of beta 1 from the fitted value that I get, and this is its standard error that you get from the R output. This is from the R output. It's easy to see that. You'll find that in every case you will get the value of the parameter, its standard error, and the z value, which is essentially the value of the parameter divided by the standard error, and so you've got the standard error available to you. And here is the calculation for the confidence interval for the beta 1. If we look at a k-fold increase, a two-fold increase here, we said what happens is going to be everything, it becomes 2 to the power of beta. So 2 to the power of beta in this case, if you want to transform the confidence interval to find what happens, if you double the area, what happens to the odds ratio? The odds ratio is going to be transformed in the same way. So it's 2 to the odds ratio we had before. And the odds ratio here, the calculation for the confidence interval was we had before, saved in this Kunit.ci, so it changes by the same amount here. So what you've got here is this idea that the confidence interval, so this is a bit complicated, for a half-fold increase, sorry, for double-fold, two-fold increase here first of all, the confidence interval will change by a factor between here and there. So we're looking now at what happens if I change or double the area, by what factor will the survival of the odds of survival change by? It's going to be changing by a factor that lies between here and there. So this is now going to be an estimate of this 2 to the beta 1 hat that I'm looking at. The previous one here, I had this one corresponds to the confidence interval for beta 1 hat. I've got 2 to the beta 1 hat, so I raise 2 to the power of the interval from before, and I get the answer for the particular factor by which it changes. This is a confidence interval for the factor, yeah? Change by a factor between those two. And similarly for the other one here, for halving that, you'll find it'll increase in this case, as you'd expect. It'll be bigger than 1 here and less than 1 there. Any questions? There is a bit more complicated things, but have a look at them afterwards if you wish, and try and understand what's going on there. These things are important in what happens as you change things to understand how the behavior will be, in this case, of extinction versus area. Model assessment. Now the problem here is, as far as residuals are concerned, and if you try this, you'll find this is the case here. The problem is that the residual is defined as the observed minus the fitted. Now, the observed value, because it's a probability, can only be 0 or 1. Or if you like, observed value, sorry, being the data itself, binary, the data is 0 or 1. What I'm fitting here is the probabilities over here, which lie between 0 and 1. So the data is between 0 and data is 0 or 1, whereas the observed value is between 0 and 1. If we take a look at the residuals from there, what you're going to get is these two parallel lines. Essentially, that look like this. I think they look like this. So when my observed value is actually 0, and my fitted value is actually 1, probability, my fitted value or the estimate of probability can be 1, then my observed minus expected is going to be 0 minus 1, negative 1, which will be the other way. At negative 1. Otherwise, it will be at 1. So, you're going to get these parallel lines that look like this essentially. Not quite going that far, but in the idea here, it will be parallel lines that look like that, similar to that. And so, they don't give us any information at all. There's nothing much here. You can't really see much as to if the model is misspecified or other problems with that. So, we try to reduce that to get some other kind of residuals from there. So, the usual idea is what we call the Pearson residuals, the deviance residuals. And the Pearson is what's commonly used. It's the observed minus the expected. And the expected here is based on my fitted value of pi I hat. Mi pi I is my expected in this case. And this is all over the standard error or standard deviation, if you like. So I've standardized this. So these are standardized Pearson residuals, and these are going to be continuous. So I can look at those and try and work out from there if I've got some kind of behavior, outliers or whatever else here. And so this will have mean 0 and standard deviation equal to 1 because I've standardized this whole thing. So here the Pearson residuals, simple to calculate by just the formula. Implement the formula, you've got it here. And you can see, actually this is not by formula, this is actually by extracting it from the fitted model itself. So is the residuals from the model that we fitted here, and the type of residual is Pearson, so it extracts it for us here. And here is the plot of the residuals. It looks very similar to what you would expect to see or you would like to see for the usual normal regression. It's something centered around 0 here, and there's a random scatter of points around it here. So in that sense, it behaves in the usual way as you expect residuals to behave. And here there's nothing particular you can see, no particular outliers or no particular patterns, so that all looks good here as far as your residual analysis is concerned. Something wrong with my code here. Actually, the histogram didn't plot out, unfortunately. I thought I had it. I'll fix that. Surprised. The other thing with histogram, of course, again, is the idea is to see whether it looks like a normal distribution, and if it looks fine, well behaved, the outliers will be fine. I'll fix the code here. I can't see what's wrong with that, but I'll have a look at that. I think I might have to. What am I about here? Okay. Okay, so now getting to the last part, which is looking at the deviance test. So we had the idea here essentially being deviance test actually is for whole models. I can compare two models this way, and essentially that's what I'm doing here. I've got the null model, which is essentially saying that my log odds ratio is a constant beta naught, and my fitted model here, or the full model, is where I've got beta naught plus beta 1 times the log area. So I'm comparing between models in that case here. As I was saying here earlier, this idea is I'm looking at the difference in deviance over here, and so along with the difference in deviance also I get a difference in the degrees of freedom between the two models, the null model and the other model. I want to look at the degrees of freedom. Now in this case, if I look at this, and there's some errors here, I can see why that would be the case. I thought I had looked at this beforehand. Never mind. I'll fix those as I go through. So here, what we do here is, for the null model, these are the degrees of freedom. Sorry, that's the null deviance, residual deviance. And for the full model, or the fitted model, is 12. The degrees of freedom is one different there because I fitted one extra parameter here. Here I've got beta 1 is not equal to 0, and here I've got beta 1 equals 0. So there's no beta 1 in the null model here. The degrees of freedom between those things is equal to 1, and so the difference in the deviance comes from a chi-squared. It wouldn't be 16, it's a 1 distribution. So if I'm comparing those two models, the null model with the full model, the degrees of freedom have a difference of 1. If I'm looking just at the full model itself, by itself, and saying, all right, what is here my residual deviance, and I want to see whether that residual deviance itself is small enough to decide if the model is good enough, I can do a whole model test. But I'm doing here a test for just the comparison between those two. I'm sorry, the code has failed me, but I'll look at this again. So the idea here is that the difference in the two residuals, the deviances over here, would be what I'm looking at, and the distribution of the difference is a chi-squared 1, where 1 is the difference in the degrees of freedom between those two particular models. I can do the test directly here. Now, this is so if you actually go ahead and look at the numbers over here, you'll find that the degrees of freedom here is 1 difference, and the difference in the residual deviance over here between the null and the residual deviance in the fitted model is something like 33 odd. Now chi-squared 1 has a mean of 1 and a variance of 1 as well, and this is actually quite large, so you'll find a p-value that's quite small. In this case, then you will accept the residual, you'll reject the null hypothesis and accept the alternative hypothesis, if you like, to say that beta 1 isn't 0, the same conclusion as before. I'll check those numbers again and see what's happening there. I'll fix them up so you can see them afterwards. But you will find that's the case, that the p-value will be quite small in this case. Now, common limitations of the model we're looking at here. The problem with what we call the Walls test, or the Walls statistics for taking a look at the hypothesis test for the individual coefficients, is that it can be quite conservative. If you have especially a large number of variables in the model relative to the number of successes or cases where that you have in the data here. So remember, what we've got here is we have binomial observations only, and you might only have 2 or 3 observations on the binomial distribution. If that's the case, and you've got something like 3 or 4 variables you're fitting in the model, then that can be a problem. And of course, the other problem always is that if you've got higher correlation between the explanatory variables, something that's called collinearity, and that's a problem even in normal regression. Then that can also cause a problem with, as it says, the standard error increases. So sometimes you'll find when you fit these models, if you have a look at it, things might look good if you look at the last column only of p-values. You've got lots of significant things. But it's always worthwhile looking at the second column of standard errors. It doesn't happen very often, if at all, I haven't seen one at least, in the normal regression. But in this kind of log linear models with Poisson and with Binomial, you'll find sometimes what you see is your standard errors are huge. Things like 10 to the 5 or 10 to the 6, huge standard errors. That alerts you straight away there's a misfit there somewhere. It may be because of this idea that you've got explanatory variables that are correlated. And so you need to look at the model more carefully. This kind of model fitting is actually very tricky indeed. And so what I might do is, one thing to do is omit variables one by one until you find the standard errors fix themselves. And once they start fixing themselves, where they become more in the right kind of range, you can realize which variables causing the problem and omit that from the model to start off with. Fit with the model without those variables. This is a common thing you find in large data sets when you're trying to fit these kinds of models. So these are the problems with the walls, actually the fitting the model in this case here, because what you find is the model fitting here depends on maximum likelihood equations, and the problem is you've got several things to estimate. I've got beta naught, beta 1, beta 2, and so on. So what you have is simultaneous nonlinear equations to solve that can't be solved analytically. They must be solved by iteration, and so you find these iterative methods like Fisher scoring or Newton-Raphson. Sometimes you'll find here in the R output, it will tell you how many Fisher scoring iterations were required for fitting the model. And if I can go back, I'm pretty sure you'll find this over here somewhere when you fit the model. I'll skip that. But you'll find in the bottom there, it'll tell you the number of Fisher scoring iterations required to fit the model. Sometimes it's just 2 or 3 or 4, sometimes it can be a lot more than that. And so sometimes you also will find that your model won't converge, because the default in R, I think, for the number of iterations it takes is something like 10 or something. So if you look it up in R, you'll find there in the regression model fitting in the actual command itself, after you've got things like data equals whatever, you can put in an extra bit that says max it equals, say, 100. So if the model fails to converge, it's because it hasn't gone far enough. It has the default setting of the maximum number of iterations is 10 or something. If you increase that, the model will converge. If 100 is plenty, that I've found in my experience, 100 looks to be what works in most situations here. So if the model refuses to convert, there's a problem. So there's several things you might find when you fit real data with this. One is large standard errors that you'll find by looking at the second column. Things like 10 to the 10, 10 to the 5 are really huge standard errors. You don't expect that. The second is it might not converge. And the third is you might find sometimes when you look at the R output, you've got some NAs in the fitted place, so it's expecting to see output which relates to the actual coefficient and everything else. It'll just say NAs, and that's because there's something here. Either you're overfitting the model, you've got some particular problem where that particular variable aligns exactly with some other variable, and so it can't estimate them both. Or you've got too many variables in the model. All those kinds of things you might see when you fit these things. Now, luckily, I'm pretty sure that the kind of data you will be getting here, you won't see those. But in real life is quite a bit different. So watch out for those kinds of things as you try and apply these models. Here are some common limitations. What you might find is that any zero cell counts in the cross tabulation of a categorical response variable against the response variable. So in other words, if I'm taking a look at, say, something like let's take a look at where I've got income groups of, say, low, medium, and high is one of my variables. And I'm taking a look at, make it easy, male, female. So I've got here 10 males in here, and 20 males in here, and 30 males in here. And I've got 30 females in here, and 50 females here, and nothing here. So you can see, because I've got no females in the high region over here, I can't fit a coefficient for females in the high region. Can't be done, right? So that's a problem you'll find. It won't fit it. There's nothing to estimate there because there's no data there. So that's another thing you'll find where you get NAs as well happening here. And that's not uncommon. If you've got categorical variables in your data that are explanatory variables, you might find they don't quite match up with your output. It's always worthwhile tabulating these kinds of things. Look at some tables beforehand, before you fit the data. The unfortunate thing is, because you've got a package like R, which just pressing the button you get models fitted, people don't look at data itself, and that's where problems arise. You get lots of problems because the data doesn't behave itself the way you expect it to behave itself. Yeah, so be careful. Look at cell counts or counts with categorical variables beforehand. And that also applies when you're taking a look at, for example, interaction terms as well. To have interaction terms, you must have each level of one variable occurring within the levels of the other variable. If there's some missing, then again you can't have interaction terms being fitted. Sometimes what you get is perfect fit. You've got the explanatory variables aligns exactly with the successors. Yeah? And so what you get there is it will tell you that you've got fits with probability 1. So in the output you'll have essentially all the p-values will be 1 essentially, that the thing fits perfectly, and in other words you can't do anything more with it. And so sometimes you get that where some of the variables or one variable in the data actually aligns exactly with the occurrence of ones and zeros. So this particular variable predicts exactly what your data itself is, your response variable is. You see that as well quite a bit. This is known as complete separation. You will find this, as I say, if you look at enough data, you'll find this kind of things occurring. I might actually pull some out and put it in a lab somewhere if I am able to do that quickly. Otherwise, just be careful that these things will occur if you fit data. Now, if you do fit data and think to these kinds of models and you get some problems, always come back and look at these notes if you want to see what's going on. But you can always search for this in Google as well. They'll tell you what's going on with Google here. There's another thing that you'll find here. The dispersion parameters, looking at dispersion here for binary is taken as, binomial is taken as 1 here. So what does it actually mean here? What does this dispersion parameter mean? You'll find that for this log linear model we're fitting here, the binary model as well as Poisson model is taken as 1. And what's the problem here? Well, it actually comes from what we said earlier. We're looking and saying that these logistic regression models apply to the probability models from an exponential family. So in that family, mathematically speaking, there's a parameter called phi, which is taken as 1 in these situations. Now, the problem occurs when it says it's taken the parameter to be 1, right? It says taken to be 1. It assumes it's 1. But what if it's not actually 1, if it's something else? And you can find out if it's 1 or not 1, and we'll see that later on. The problems arises when you've got things here where so this is actually looking at saying that my variance or my spread in the data, dispersion meaning spread, is how I expect it to be. I'm taking my parameter, phi parameter to be equal to 1. But if the variance is too small or too large, your model doesn't fit very well. You get problems with this. So this is called under dispersion, when the variance is too small or too large than expected, than it should be from the model itself. And how do you actually adjust for that? We'll see that later on. Again, that's something you can test for and check, and then you can work it out from there as to whether what you've done is reasonable or not. And a lot of information is contained in these kinds of things here. The residual variance here with degrees of freedom contains a lot of information about this thing here as well. We'll see how that works in the next few lectures afterwards. All right, almost finished with this idea here. I'm going to skip the last few slides. Essentially, it says this idea of conditional regression, where essentially what you're going to do is you're going to have different regression models for different parts of the data. So you might have a model for the males and one for the females with everything else included, but separate the thing by males and females. In other words, what we call you stratify the data. So how do you fit that here? You'll find this afterwards. We'll probably find some of these in some of the labs, I think, maybe. I'm not sure, we'll see. But you've got this thing about fitting the same kind of model using this C-logit function, where you can indicate which part of the data you're going to fit and how you're going to organize that to have two different models for the two different parts. Are there any questions so far? Yes?
On slide number 43, you said it's the explanatory variable for 20 format.
Yes.
What should we do then?
What you do again is you drop the variables one by one, right? You've got something like a model with 10 variables. Two ways of working around it. Start with just one variable in the model and then build it. You'll identify where the problem is. Or take them off one by one and you'll realize what's going on here. Yeah? So in real data, it's just like, for example, the kind of stuff I work in quite a lot is you get something like 50 variables to fit in there. Massive, yeah? Something like a few thousand data points, 50 variables to fit in there, 50, 80 variables to fit in there. So you're going to have these kinds of problems there for sure. It's massive, yeah? So you'll find where you've got problems with the standard errors being huge, or the NA is occurring, or perfect fit. All those things occur, yep.
You said when the standard errors get big, that you should probably drop the variable of the model. Is that also a reason that we can translate it, maybe?
You may be able to, but the first thing is to find out where the problem is by taking variables off one by one. Yeah? Fitting models is very tricky stuff. Any more questions? Well, I'm going to spend some time on a video for the next 15, 20 minutes. It's a long video, but I'll cut out some of it if I think it's too long. But this is dealing with some of the kinds of things I would expect many of you will actually work on later in your life. And this is by Alas. I don't want to turn everything off. What's going on here? Turn this all off. Let's see how the video looks like anyway. I think we'll be able to see it. This is a last by the name of Hannah Fry, an English girl who did a PhD in pure mathematics, but actually is now working in this area of what's called social mathematics. So have a look at this. I think you'll find this interesting. As I say, I shall try and reduce this if it... what's going on here? Why can't I play this? Yep.
Thank you. Thank you very much. Right, I thought I'd kick off by telling you about one of my favourite science studies. It's a little unusual study into the diagnosis of breast cancer. So back in 2015, a scientist took a group of 16 complete rookies, and they decided to try and teach them how to diagnose breast cancer based on pathology slides like this one here. So the idea was that at the end of the training period, these testers would be able to look at slides like this and tell whether they were malignant or benign. Now, despite the fact that normally it takes years to train to be a fully fledged pathologist, these testers who had never diagnosed any kind of cancer before in their lives actually did astonishingly well. So after only 2 weeks of training, they managed to get about 85% of these slides correct, which is astonishing, right? But the really amazing thing about this study wasn't the performance of the testers, it was their identity. Because these weren't medical students, they weren't strangers off the street. They were, in fact, pigeons. Now, I know it's a bit difficult to imagine pigeons diagnosing breast cancer. So what I have here, I've got a little photo here. This is proper science, by the way, people. It's real science here. This is their little laboratory. They had a little screen on one side where the slide would pop up, and they would peck on one side if they thought it was malignant, peck on the other side if they thought it was benign, and they'd get a little treat at the end if they got it correct. Now, these birds did pretty well, right? But the paper talks about one slightly stupid bird who didn't really understand what was going on. And even by the end of the testing, was just kind of pecking randomly at the screen. But if you take that bird away, It turns out that although these birds could get 85% of these slides right on their own, if you combined the votes from all of the birds together, so flock sourcing your diagnosis, as it were, thank you, more of those to come, then actually the accuracy of these pigeons shot up to an incredible 99%. And that is a number that is comparable to what a fully fledged pathologist would be able to manage. Now, I don't think that we have to particularly worry about our hospitals being overrun by bird doctors just yet. But I do think that there's a reason why I wanted to start with this example, because I think it actually illustrates a really important point. Because I think that we like to imagine ourselves as humans as being uniquely capable of a whole range of different things, that we're uniquely talented, really. There are some jobs that we and we alone are capable of doing. And I think that this example really clearly demonstrates that that's just often not the case. And if you can train birds to diagnose cancer, why can't you train a computer to do it too? And I think this is really something that has changed in the last couple of years. I think that we've really started seeing stories about machines being able to outperform humans in things that we thought were our job and our job alone. And I think that, you know, the stuff that algorithms can do now is just incredibly impressive. I mean, we have algorithms that can catch serial killers. We have algorithms that can drive cars, you know, even algorithms that can diagnose cancer better than pigeons can, right? But, you know, ultimately, I didn't really want, the book that I've written and the talk that I want to give you today isn't really about algorithms. It's really about humans. It's about how we fit into all of this and really what we want our future to look like. Because I want to just tell you a little story about, but I think that this was the moment in my career when I realized that when it comes to algorithms, you can't just build them, put them on a shelf, and decide whether they're good or bad in isolation. You have to think about how they're actually going to be used by people, so both, you know, now and longer term in the future. And of course, there's these big ethical questions like, you know, algorithms being turned and being used by police states, but there's also much smaller stuff. Because I think what I've come to realize is that if there is one thing that's absolutely for sure, it's that you can't rely on people. Let me explain what I mean. And I think the most sensible place to do that is with some Japanese tourists who went on a trip to Australia, as this story will show. So, okay, this group of Japanese tourists, they decided, while they were on their holiday in Brisbane, they wanted to go on a little road trip. And they wanted to go from where they were staying, which was here, and visit this very popular tourist destination over here. So they hired a car, popped into their sat-nav, and it said, well, it's basically a straight line, which is great. Slight problem that you can't necessarily see from this satellite image is that, unfortunately, there's a great big whopping body of water between the two. Now, in fairness to these Japanese tourists, they didn't notice this immediately. Perhaps they didn't speak English particularly well and didn't notice that, you know, the word island appeared on the name of the place that they were trying to drive to. But I think you could forgive that. But you would think that once it came to actually trying to drive on water, they would know it was time to overrule their machine, right? Apparently they didn't. I think this was probably quite embarrassing when someone had to wade out to come and help them. Definitely embarrassing when they had to abandon their hire car. But most embarrassing of all was about half an hour later when an actual ferry sailed past. But the thing is, I think that we can all chuckle at the silliness of this story. But, you know, I think I've come to believe that actually these Japanese tourists aren't really alone, because I think when it comes to placing blind faith in a machine, actually, this is a mistake that we're almost all capable of making. And of course, there's really big examples where we've let algorithms take the driving seat that aren't necessarily deserving of our trust. The big story about Cambridge Analytica earlier this year being a really key example. But I think if you look closely enough, you will see this story over and over again of people just giving up their power to a machine. But I think that we're all aware now that by now, you really can, if you have enough data on people, you really can work out all kinds of different things about them. So you can work out what they're going to buy, you can work out which way they're going to vote, but you can even work out whether or not they're going to go on to commit a crime in future. And that's what this questionnaire here is from. This is from an algorithm that a so-called recidivism algorithm that is used when defendants appear in court, and it's used to predict whether or not that defendant will go on to commit a crime in future. And it's used by judges. This example's from America, but this is something you find around the world, including in the UK. And it's used by judges to decide who should be awarded bail, and in some cases to decide how long someone's sentence should be. Now, I imagine quite a few people in this room have sort of heard of this happening already, and I kind of wanted to get your take on this. So I want you to imagine that you're the one in the dock, right? So I want you to imagine that you've committed a crime. It has to be something that you did. You've got to be guilty, right? Otherwise this doesn't work. So you've committed a crime, you're standing in the dock, and a decision needs to be made about your future. Who would you rather presided over your future? Would you rather it was a human, or would you rather it was an algorithm? You know, these algorithms aren't perfect, and I think it's only the case if we...
That's another question here. If you're in the dock yourself, as somebody who's committed a crime, and you're going to be sentenced or tried here, would you rather have a judge presiding there or a machine algorithm? Who says a judge? Who says the machine? Machine, why? More accurate? Any more? Why a judge? Or lack of? Yeah, exactly. One thing is that machines don't discriminate, right? Algorithm can. Or can the algorithm discriminate? Depends how you build the algorithm, right? It's an unclear case. You see, there's lots of research in this area that shows that you bring similar cases to the same judge and they'll decide differently. You can bring the same case to the same judge on different days, they'll decide differently. Yeah? And if a judge who's given maybe 3 or 4 not guilty verdicts will tend to go guilty for the last few to balance it out a little bit. So all these kinds of things, whether the judge is tired or hungry or whatever else, had a fight with his wife or her wife, or the local team's lost, those kinds of things all affect the judge's mood and how they decide. Algorithms, on the other hand, are, as you say, consistent at least, right? Except they can also cause problems. So
we can trust the human judges to know when to overrule the algorithm.
So here it is, when you've got an algorithm with a judge, helping or assisting him or her.
Because the AI or these algorithms, they're going to make mistakes, right? They're going to make calamitous mistakes. Let me give you an example. There was a story about a young man called Christopher Drew Brooks. Now, he's a 19-year-old man from Virginia, and he was convicted of the statutory rape of a 14-year-old girl. Now, they had been having a consensual relationship, but she was underage, and that's illegal. So during his trial, an algorithm assessed his risk of reoffending, and it determined that because he was such a young man and he was already committing sexual offences, he had a very high chance of continuing in this kind of life. So it deemed him high risk and suggested that he be given 18 months jail time. Now, in theory, there's nothing necessarily wrong with that assessment. But this case does really illustrate, I think, just how inconsistent these algorithms can sometimes be. Because this particular algorithm put so much weight on this young man's age that, in fact, had Brooks been 36 years old, that would have been enough. In fact, putting him at 22 years older than the victim there, which I think by any possible metric makes this crime much worse, right? But that would have been enough for this particular algorithm to kind of tip it over the edge and suggest that this young man was instead a low-risk individual and suggest that he escaped jail entirely. Now, you would hope, I think, that in a situation like this, the judge would have the foresight to overrule an algorithm like this, right? And to rely on their own instinct instead. But it seems that judges are actually a lot more like Japanese tourists than we might imagine. Because in this case, and many, many others like it, the sentence of the individual was increased on the say-so of this logically flawed algorithm. But there is another problem with these algorithms, something that you actually spotted there, talking about kind of bugs in the system. And that's really that they don't make the same mistakes with everyone. They make mistakes, but it's not kind of uniform across the board. And I think what we've really realized in the last couple of years is that the algorithms that we've invited in to make decisions in our lives, they have these all kinds of deep hidden biases. And I think that really part of the way out of all of this mess is by acknowledging that artificial intelligence and algorithms, they're just not going to be perfect, right? And that's because they just don't understand the world in the same way that we do. They don't understand context, and they don't understand nuance. And that, I think, is something that has never been clearer than when you ask an algorithm to recognize what's contained within an image. So this is an experiment. Here we go. This is an experiment that was done by Janelle Shane, the blogger Janelle Shane. I've repeated it here for you. She noticed something a little bit weird when you upload photographs like this to image recognition software that will automatically label your photos for you. So I've done this one with Microsoft Azure. Okay, here's the label that it gives this particular photo here. It says that this is a herd of cattle grazing on a lush green field. Now, I can definitely see a lush green field. It looks very lovely. I mean, I've spent quite a long time looking at this photo, and I failed to find any cattle contained within it. And that does make you wonder, is this image recognition software hallucinating farmyard animals? Well, let's give it another go. Okay, so let's try it with this one here, this image here. This one, it labels as a sheep standing on a lush green field. It's got quite a thing for lush green fields, this particular algorithm. But okay, does it really understand what a sheep is then? I kind of makes you wonder, does it know what a sheep actually is? Well, let's try. Let's take a sheep in a slightly more unusual situation. Try that. This one, it labels as a cat sitting on top of a wooden fence. Take a farmyard animal, put it in the arms of a child. The algorithm thinks, well, that can't possibly be a living creature. Take farmyard animals, put them in a tree, and it thinks, well, they must be birds. And my favourite of all is if you take those farmyard animals, leave them where they are, but paint them pink, it thinks that suddenly they must be flowers, which is quite nice. Although, let's be honest, a far more sensible explanation for what's going on there than why those sheep are actually pink. But, you know, perhaps all of this stuff, perhaps it doesn't really matter. But I think when image recognition is used to start to really change people's lives, it starts to become actually quite important. Let me just tell you one one last story about a story of something that happened in Idaho. So back in 2014, there were 16 disabled residents of Idaho, and they received some unexpectedly bad news for the day. So the Department of Health and Welfare, they just introduced this new budget tool. And the idea with this budget tool was it was going to automatically calculate how much each of these residents, how much state benefit, each of these residents were entitled to. Now, these were people who had quite severe disabilities. So this money was essential to making sure they could keep their independence, really. They qualified for institutional care, but were being cared for at home instead. So one by one, they each went into the State Department to find out how much money the algorithm decided that they were entitled to. And weirdly, some people found out that they actually were entitled to much more than they'd got in previous years, while other people, as you might expect, ended up having deficits of sort of tens of thousands of dollars. Now, from the outside, no one could work out how the hell this thing was making its decisions. It looked like it was essentially just plucking numbers at random. But the problem was it was kind of impossible to argue with this computer. So the people who worked for the government just trusted its output a bit too much. So in the end, the residents had to bring this class action lawsuit to have this algorithm turned over to be scrutinized. And when it was scrutinized, they discovered that this algorithm that had so much power over their lives, it wasn't some super sophisticated artificial intelligence like they'd sort of been led to believe. It wasn't this like super slick mathematical model. It was, in fact, an Excel spreadsheet. And if you'll forgive me for being blunt, quite a crappy one at that. So this Excel spreadsheet, it had errors all over the place, right? There was bugs in the data, the formulas were a mess. In fact, the maths in this spreadsheet was so bad that the judge would eventually rule it unconstitutional, right? I love the idea of there being unconstitutional maths. But I think that, ultimately, the moral of this story is that once you kind of dress something up an algorithm or as a bit of artificial intelligence, it can take on this air of authority that makes it really hard to argue with. So I thought that I would leave you with a much more positive example, I think, of sort of how to get around all of these different issues that I've raised during this talk. An example of where I think people really do understand like what the future should look like. And I want to go back to the example of breast cancer that I started with, where I think people are doing some really incredible stuff. Now, if you want to design an algorithm to diagnose breast cancer, there are two things that you want your algorithm to be able to do, okay? So on the one hand, you want your algorithm to be really, really sensitive. You want to make sure that your algorithm catches every single last tumour that's hiding amongst that vast array of cells. You want to make sure it doesn't miss any last single tumour. But you also want your algorithm to be really, really specific. So you want to make sure that your algorithm isn't flagging loads of normal tissue and saying that it's suspicious when it isn't. Okay, you want to make sure that it's really accurate in all of its assessments. So, okay, simple then. If you want to design an algorithm to diagnose breast cancer, just whack up those two dials and you're done. Except, unfortunately, it's just not really that simple. Unfortunately, when it comes to designing these algorithms, these two dials tend to be locked together. So turning one up often means having to turn the other one down. And that means you can kind of inadvertently design something that's quite a crappy algorithm. Because, for instance, there is something, a very simple algorithm that matches this profile here, a very simple algorithm, just a single line. All it does is it just says, everyone has cancer, right? Gets 100% sensitivity, certainly, but not that much use in terms of actually diagnosing people. So what you have to do when you design these algorithms, you have to just do the very best that you can. You have to play to the strengths of your algorithm. And believe me when I tell you, these algorithms have some absolutely almighty strengths. So on the subject of sensitivity, let me just give you a flavour of the kind of things that these algorithms can do now, using an example of one of my favourite data sets. Everyone has a favourite data set, right? This data here, this is some data from something called the Nun study. And this shows the cognitive ability of 678 nuns. So this was some data that was collected by the epidemiologist David Snowden. And at the beginning of the study, these nuns were aged between 75 years old and 103 years old. And David Snowden managed to persuade these women that every year of their life, they would take a little cognitive test. So being asked things like, how many animals can you name in a minute, right? It's questions like that. And what you can see here is the data for how these women performed, right? So along you can kind of get this trend of of cognitive decline as people get older, because they appear on this every year of their lives. Along the bottom there, you have the people who ended up getting dementia. And along the top there, especially the top sort of right-hand corner, that's where you've got people who remained absolutely sharp well into their older years. Now, the reason why this is one of my favourite data sets is because not only did David Snowden manage to persuade these women to take these tests every year, he also managed to persuade them to donate their brains to the project after their deaths. Now, if you're a little bit squeamish, I suggest you look away, because I'm going to show you some human brains in a second. But these are the women, these are incredibly generous women, the School Sisters of Notre Dame from Kentucky. And in a moment, you're going to see the room where all of their brains are kept, right? This wall of brains, essentially, that scientists use. Now, the reason why you want to do this is so that you can look to see whether the people who had signs of dementia in life are the same people who had signs, physical signs of the disease within their brains in death, right? So when you dissect their brains, whether you see all of the kind of lesions, all of the hallmarks of dementia having affected their brains. Now, you would think that these two things should be straightforward, right? Signs of dementia in life, signs of dementia in death. Except it turns out that's not the case. There are some people who really buck this trend. So take, for example, Sister Mary here. Sister Mary died when she was 101 years old. And as you can see from her position on this graph here, she was incredibly sharp right up until her death, doing crosswords, all of this different kind of thing. And yet, when her brain was dissected after her death, it showed all of the hallmarks of having been ravaged by disease. In fact, inside her brain, there was barely any difference between her brain and one that would appear much lower down, kind of lower down this chart. So what on earth is going on here? Why are some people able to resist showing the symptoms when they have this stuff going on inside their minds? Well, it turns out that a clue might be hiding in another data set altogether, one that was created decades before any of these women even showed any signs of dementia. Because this team also have access to the essays that these women wrote when they entered the sisterhood, when they were 19 and 20 years old. And if you do some very, very simple analysis on the language that is used in these essays, you can predict which women will go on to develop dementia later in life. So here's an example for you. This is a sentence of someone who did not go on to develop dementia. And you kind of see the complexity of the language, how densely packed the ideas are, the sort of vocabulary that's used, and so on. And compare that to a sentence from someone who did go on to develop dementia, and you can kind of see illustratively just how different they are. Now, this is the stuff that algorithms are amazing at, looking for tiny, tiny clues in seemingly completely disconnected data sets that can make really big predictions in the very long term. So in fact, when it comes to cancer diagnosis now, the algorithms that we have can't just tell, it's not that they're just telling you what's in your body right now. They can make a prediction about your long-term chances of survival based not only on the tumor itself, but in something in the surrounding tissue that we're still trying to work out exactly what it is that they're picking up on. Just incredibly, incredibly sensitive, these algorithms, right? It's just absolutely amazing what they can do. And yet remember that sensitivity does not make a perfect algorithm. It's only kind of one half of the equation. Now, on the flip side, humans, when it comes to being sensitive, we're rubbish, right? We're totally rubbish at this. I think this is something that was best illustrated by quite a mean trick that was played by some Harvard scientists on some radiologists back in 2014. So what they did, they got these professional radiologists just to see how sensitive their eyes were, and they showed them this image of a lung. And they asked them to have a look at it, and they used eye tracking software to see where they were going. And they failed to tell them, and 83% of the professional radiologists failed to spot, that they had hidden an actual gorilla inside the lung scan. Despite the fact that the eye tracking software said that their eyes were looking right at them. And if you've got professional radiologists missing gorillas, you can imagine how many tumors end up getting missed. We are terrible at sensitivity, right? We are really, really bad. We miss things all the time. But specificity, being specific, that's like our superpower. So if you have a fully trained radiologist or pathologist, they will almost never misidentify a perfectly normal set of cells as cancerous when they're not, right? Something that almost never happens. We're incredibly, incredibly good at it. So here's the idea then. Why don't we just accept that neither humans nor algorithms are ever going to be perfect, and rather than choosing between human and machine, which is kind of the rhetoric that we get so much, why don't we exploit each other's strengths and just create much more of a partnership? And this is what's happening now in the way that these cancer diagnoses are being designed. Because the algorithm never gets tired, so let it trawl through all of that data and just highlight a few key areas of concern, and then the human never misdiagnoses, so they can come in and just sweep up and have the final say. They're playing a really active role in all of this. And I think, ultimately, this is the version of the future that I'm really hoping for. I think one where we start embracing the flaws in the algorithms as well as acknowledging our own, really. And I think one where we start taking our algorithms off of the pedestals and start treating them like we would any other source of power by questioning how they work and calling them out for their mistakes. Because I think ultimately, you really can't think of technology and artificial intelligence and algorithms in isolation. You have to think of all of the failings and all of the trust issues of the people who are using them. Thank you very much.
So I'm sure you've all heard of this idea of this robot debt thing in Australia recently, where also pensioners lost quite a bit of money because of this algorithm that was used. And the problem with any algorithm, especially if it's, well, a good algorithms at least that are based on mathematical modeling, the problem is models always give you averages, yeah? They never give you extremes, they never give you specific things. They're based on a lot of data from a lot of people, and they're based on averages. Now, of course, they're getting clever because, every time you go to Woolworths and shop and you scan your card, they've seen what you've bought, your loyalty card. You see, loyalty cards aren't just for you, they're for them, of course. They've got data on where you live and how far you might go to shop, and also what you're buying, your regular things. So I've got data on myself, specifically myself, and I can see what's going on with my life in that sense. So then they'll start marketing and targeting to you. So my wife and I share my Facebook thing. I hardly go there. She goes there quite a bit. And also she says she has my YouTube account. So whenever I go on YouTube, suddenly I get these ads for clothes, which she's been looking at, and I haven't. Or my daughter uses something or buys something there, and it comes back to me. So you can see how these things are all addressed. The problem with algorithms is always going to be that people don't behave themselves the same way all the time. Today you bought Labour, next time you bought Liberal for some reason. Today you like ice cream with strawberries, next time it's going to be with chocolate, something like that. So you can't actually account for people's changes in behavior, the nuances they have. So yes, algorithms do fantastic stuff, and where they're fantastic, they should be used. But always remember that they aren't perfect. And so always you must temper what they give you and think about what you've actually got to say whether it's reasonable or not. This is something that, of course, is not just coming into the world, but in your lifetime, especially as data scientists and statisticians, you'll find this will be there quite a lot. And maybe you are the people out there who will be looking at this more critically and saying, look, don't be just blind to what you're seeing in the algorithm, what it's giving you. Think a bit more to see whether it actually is reasonable as well, whether you can evaluate the thing and make sensible decisions using what that's giving you, but tempering that through your own logic and your own thinking. I think that's enough for today. Thank you so much. We'll see you next week. Make sure you do the test before Friday. It's not a very hard test. I hope you'll spend the time and get it all done before Friday. How are you, husband?